USACO live solution explanation section for the US Open of this season. This is the last contest, and this is today's agenda. I'll first go over a brief introduction of XCamp, and then I will hand off to Alvin for the contest tutorial, and after that, Alvin will also talk about the chance of the season and also provide some tips for how to prepare for the next season, including what XCamp is offering to help you boost yourself for the next year. So my name is Yuan, and I'm the co-founder of XCamp, and I'm in charge of XCamp's teaching research, and technology platform. So XCamp is a Silicon Valley-based coding academy. We offer classes nationwide in online format right now. Our class goes from beginner level to master level. And over the years, the curriculum has been developed by seasoned coach, and lots of different very, very strong past competitors from different competitions in the US and also from China. Many of them are world-class competitors when they were in senior high school or in college. And the curriculum system is proven in several folds. First of all, XCamp nowadays is being treated as the solid place to gain the computer science and the data structure algorithm education. And also we have been having solid USCamp records since 2 years ago, since the very first generation of students. So far, the number here is actually not 100% correct. We have been, actually last year we have indeed 4 campers, and the year before we have 1. And this year, according to our newest data, we seem to have even better results. And also we have more students passing lower levels, such as gold, silver, and the bronze. The concrete number will do more aggregation and provide that later. So today's section, Alvin, who is also our USACO Grandmaster class teacher of 601, will teach the tutorial. He was the ICPC World Finalist in 2022 as well. It is the International Collegiate Programming Contest. What World Final just means that in different countries, eventually it's going to be a subset of a team got selected to the World Final to compete together. All the famous schools will appear there. Next, I'll hand off to Alvin to talk about the gold question. Given the audience of the gold section is kind of much smaller than silver or bronze, I'm hoping this can be a more interactive process, and for all the students, feel free to answer Alvin questions whenever, for example, after each of the questions, feel free to discuss a little bit more and get more engaged. Treat it more like a class, not like a live streaming section. Cool, that's all from me, and thank you. I'll hand off to Alvin.
Okay, cool. So I'll start. I'll start going through the solutions from this contest. Let me share my screen. Okay. Old solutions. And yeah, you can feel free to like ask in the middle if you have any questions about any particular thing. But yeah, with that, I'll start going over the solutions. Okay. Oh, sorry, this is lagging. 1 second. Oops. Okay. Okay, so problem 1. Yeah, so feel free to either ask in the chat or unmute. Listen, if you have any questions. So problem 1 is there's like n stalls. Okay, some technical difficulties. I'll switch to whiteboard. Okay, so you have n stalls, where n is at most 10 to the 5th. Like I guess the setting of the problem is in a hotel, and then you have m corridors, where m is at most 10 to the 5th. And stall I has color CI. So 1 is less than or equal to CI less than or equal to n. And each stall has a key of color SI. So key with color SI. And you also have the constraint that 1 is less than or equal to SI less than or equal to n. And you're allowed to do the following. Can do the following. So you can do the following: pick up a key from the current cell. Yeah, just you can pick up a key from where you are, or you can drop a key. And you're allowed to hold multiple keys, and you're allowed to have multiple keys in the stall. Another option is move to a neighboring stall. So if the conditions on when you're allowed to move to a neighboring stall is if the stall you're moving to is equal to 1, then you can always move in. Otherwise, you must possess a key with color equal to CI. So I'll go through an example, but basically, the goal is you're given Fi, so given Fi, which is like the final permutation of keys, goal, make all the keys equal to Fi. I'm gonna change the whiteboard. But yeah, any questions about what the problem is about? Yeah, actually I'll just keep this whiteboard. Yeah, that's fine. So there's n stalls and m corridors. I'll go through an example. So let's just say you have 2 stalls, right? So this is stall 1 where you start at. Oh yeah. I guess, yeah. So you're also starting at stall 1. Stall 1. And the goal is to make all the keys equal to Fi and then go back to stall 1. So I'll just go through an example. So you're at stall 1. And then let's just say this is stall 2. And then this key has, so the color is equal to 1, and then the color is equal to 2 here. And then you have a key with color 1, and then you have a key with color 2. And then like F, which is like the target, is equal to, so you want to swap the keys to 1. And to do that, you could pick up a key from stall 1, and then you could go to stall 2. So in the next step, you'll be like this. You'll be here, and then stall 2. This is key with color 2. This is key with color 1. This will be empty, and then you drop this key, and then you pick this up, and then you go back. So yeah, that's the problem statement, and I'll explain the solution. So there are a few observations. So basically, so it never hurts to pick up a key from where you are and then go to the neighboring stall. So let's say you're here and then there's a key at the stall. It never hurts to pick it up and go to a neighboring stall. Right? Let's say you picked up this key and then you move to this stall. You can always reverse this operation because in order to enter this stall, you had to have the key corresponding to the color of the stall. So you can always reverse this operation. So it never hurts to pick up a key and explore, right? So you start at stall 1, right? So the idea is to like try to explore all the stalls. And once you like explored everything, then there will be other stalls around you that you cannot reach just because you don't have the key of the respective colors, right? So yeah, so the first part is to explore and then pick up all the keys. And then I'll explain in a bit how you actually explore. But after that, you'll need to drop the keys at the correct locations corresponding to FI. So how do I explore all the stalls? So you can think of this as like, let's say I've explored this amount. So I'm at the stall number 1. It must be the case that S1, if I want to like visit neighbor I, it must be the case that S1 is equal to the color of neighbor I. So let's just say that I explored like some connected component that contains stall 1, and then I have all the keys. So these are everything that I've explored. And then these are things that I haven't explored yet. The way to reach one of the neighbors is if like the color I is in one of the keys you're holding. One of the keys you're holding. And to do this, you basically want some kind of queue to keep track of the neighbors that you're trying to visit. And yeah, so basically queue int q n. And then once you have a key of a particular color, so key with color C, then you can start visiting everything corresponding to QC. Right, and then you also want, so this is one thing, when you see a new key with the color C, then you can look at what new stalls you could visit. And then also when you visit a new stall or when you see a new stall, you also want to keep track of what colors you've already, of what colors of keys you already have. So you can have another array has color N. So has color I means that you have a key of color I. And when you see a new neighbor, then this should be able to tell you whether you can visit that neighbor. So to summarize, you want it doesn't hurt to try to visit as much as possible and then have as many keys as possible. So this is the first part of the problem. The second part of the problem, so the first part of the problem is given all like SI values, picking up the keys and exploring as much as you can. And then the second part of the problem is to try to drop the keys at places corresponding to FI. So Step 2, drop the keys. And one key observation is that this problem becomes much simpler if you go backwards. So let's just say I'm at the end state. So at the end, I've gone back to stall 1, and then this key is F1, and then this is stall I. This key is Fi. And then I want to reverse the process to get to the stage where I was able to visit all these vertices and I was carrying all the keys. So in order to leave a stall, so in order to leave a stall, I must have a key. This is when you're processing it backwards. So in order to leave a stall, I must have a key equal to the color of the current stall. And when I'm going to a new stall, I want to also be able to exit it. So basically, this is basically the same as the previous step, the previous problem we were doing. So basically, I want to have a key with color equal to the neighbor. So this is basically another kind of the queue solution that I talked about in step 1, right? So I'm just reversing this process, and then I'm just trying to visit the neighbors such that all the keys, the color is equal to one of the keys I'm holding. So this is the exact same problem as step 1. So the answer is yes, if I can visit everything that I visited in step 1. Oops, sorry. Okay. Answer is yes, if I can visit everything that was visited in step 1. No otherwise. All right, any questions? Yeah, so to summarize, I try to visit everything while picking up as many keys as possible. And then I try to drop the keys, and it ends up being the same problem when I try simulating it in reverse order. But yeah, if there are no questions, I'll move on to the next problem.